Hello, Calculus. Today we're going to talk about section 6 on our series. Today we are going to learn about alternating series and what it means for a series to be conditionally convergent. This is actually going to be our last section that learns a new test for convergence. So we've learned a lot of convergent tests, and so then we're going to review those today as well. So our alternating series will be adding and then subtracting terms as they go. So each term is going to rotate positive, negative, positive, negative. So as we're adding those together, our sum's going to get bigger and then smaller and then bigger and then smaller. And what's going to happen is we're looking for the sums of those to settle in on some value shown by L here. So our first term, S sub 1, and then our second term is negative. So we actually end up back at S sub 2. And then add on S sub 3, which would be positive. Then S sub 4 is negative, so we bounce back, and so on and so forth. And what we're wondering is, are we zeroing in on some total sum that we could call L? So what the alternating series test says is that if we have all three of these conditions satisfied, the alternating series will converge. It's actually one of our easiest tests to tell if we have convergence. So the first thing is it says that the U sub n's are all positive. Another way of saying this requirement is that the terms have to be strictly alternating. That we have a positive, negative, positive, negative, positive, negative, positive, negative. Okay, so all the terms are positive. The only thing that's changing is that we have that negative 1 to a power multiplier in there. So then, again, another way of saying that is it has to be strictly alternating. If you ever end up with two positives in a row or two negatives in a row, you cannot use this test. The second condition is that at some point, the terms have to become not increasing. It doesn't have to be right away, but that at some point in the series, the terms will become non-increasing, right? Still doesn't necessarily mean decreasing, but the terms have to be not getting bigger after some point. And then our third one is that the terms themselves have to have a limit of 0. If the terms themselves are becoming 0, then that is our third one. So if all three of those are met, then we can say that the alternating series will converge. I mentioned before the most famous alternating series actually is going to be our alternating harmonics. So the first picture, picture A, shows our harmonic series. So remember that is the series of, I'll write out what it looks like in its series form. That's the series of n beginning at 1 and 1 over n. So we've got, then the terms of that are 1 plus a half plus a third plus a fourth plus et cetera, et cetera, et cetera. And we said that that series is divergent. And that's what that first picture shows, is that any number you pick m, we could say, well, no, eventually we're going to get a total bigger than that. Whereas in B, this is our alternating harmonic series. Our alternating harmonic series is going to have negative 1 to the n plus 1, so that our first term will be positive, and then 1 over n. So we start out, first term is positive 1, then the next term is negative 1/2, then positive 1/3, and then negative 1/4. And as we add together to find those cumulative sums, you can see what's happening there, that those are actually zeroing in on sum total, which is actually the natural log of 2, is what that converges to. So thinking through the three requirements of our alternating series, the terms are strictly alternating, positive, negative, positive, negative, positive, negative. After some point, the terms themselves are not increasing. So then we're not thinking about the positives and negatives, but just 1, 1/2, 1/3, 1/4, 1/5. Those are not increasing. And if we take the limit as n goes to infinity of just the 1 over n part, not the alternating part, but just as the 1 over n part, that is becoming 0. So the terms themselves are becoming 0. So it meets all the criteria for the alternating series, and it is therefore convergent. So we could actually estimate what our alternating series would add up to. This says that the sum of the terms will have an error that is less than the absolute value of the next term. And it'll actually have the sign of whatever that next term is, that first unused term. So we can actually not only know if an alternating series will converge, but we can know pretty much what it's going to converge to. A series that is convergent, but not absolutely convergent, is called conditionally convergent. So in our last lesson, we learned about absolute convergence, that we could take an absolute value of a series and see if that converges. And we said that absolute convergence implies convergence. So if we take the absolute value of something and it converges, then we can say it converges with its negatives also. But we said that that was a one-directional statement, and that's where this comes in. If the alternating, or the series with negatives, converges, but the absolute value doesn't, it's conditionally convergent. So that alternating harmonic is our classic example of conditionally convergent. The alternating harmonic does converge, but its absolute value does not. So we say that it is conditionally convergent. We are not going to worry about rearranging terms, and so then here is a summary of our tests. So we learned about the nth term test only tells us divergence. If the terms are not becoming zero, we can say the series diverges. If the terms are becoming zero, we cannot say anything about it. We learned what a geometric series is and when that converges. Geometric series are really helpful, and we can actually find the sum of a geometric series. Remember that the sum of an infinite geometric is a over 1 minus r. But that only works if the series is totally exponential, then, really, is what a geometric is. We have a p series. The 1 over n to the p will converge if p is bigger than 1. That's a very helpful rule to look for, and that especially helps with our comparison tests. If we have series with non-negative terms, we could try integrating maybe, or we could try one of those comparison tests, or we could try a ratio test. We did not talk about the root test in our course, so we would stick with ratio. Ratio test especially helpful if there's factorials involved. If we have some negative terms, then we could look at taking an absolute value and doing any of those tests above. If we not only have some negative terms, but it is exactly every other negative term, then we can do the alternating series. So there's a lot of different series and a lot of different, if it's like this, then you could, if it's like this, then you could. And sadly, the answer to the question, how will I know what to do, is by having practiced. By having practiced, you're going to know which test is going to be the best test. And I know that's not the most encouraging answer, but that really is the only way to get better at choosing which test to do. So let's look at some examples here. All of these examples today that I'm going to give you are actually going to be alternating. So we're really going to focus on that alternating and then the idea of conditional or absolute convergence. So first, when we think about this as an alternating, we want to say, is it definitely alternating every other? And it is. It has that -1 to a power, and there's no way that the other part of the series could create negative terms on its own. And then we'd want to say, are the terms getting smaller after some point? And as we plug in 1, 2, 3, 4, yes, each term is not increasing. And then the last one, if n gets bigger and bigger, will this become 0? And the answer to that again is yes. So that means this converges by alternating series. Now we want to say, well, what would happen if we took the absolute value of it? So if we took the absolute value of this, then we'd be talking about the series of just 1 over the square root of n. That's actually a p series with a power of 1/2. A square root is like 1/2. So that we learned p series are divergent if that power is smaller than 1 or equal to 1. So because the absolute value is divergent, but it converged with the alternating series, this is where we combine those two ideas and say that it is conditionally convergent. Okay, so this is a conditionally convergent series, much like the alternating harmonic. So then in our next one, let's say that we have this series here. So we'd want to, again, think about that alternating series. We've got every other term will be negative because of that power of -1. The terms are going to be not increasing, and as n goes to infinity, the terms will become 0. So it meets all of our criteria, so that means it is a convergent alternating series. Now we want to say, well, what about if we took an absolute value of it? If we took an absolute value of it, we would just have 1 over n squared. Well, that's a p series with our power equal to 2. And that is then convergent. When the power is bigger than 1, then we have convergence. So it converged with its negatives, it converged without its negatives. This one then we're going to call absolutely convergent. It is absolutely convergent. All right, for our next example, I'm going to look at this one. Now, if that n was not there, it was just the 3 to the power of n, but not the extra multiplier of the n, it would be geometric. So then we could approach this as a geometric, but with that extra n there, it is no longer geometric. So first we're going to think about it as alternating. So we do have that -1 to a power, and there's no way that the rest of it could create any negatives on its own. So it will be strictly alternating. As n gets bigger, the terms will not be getting bigger. And as n gets bigger, the terms will actually be becoming 0. So it meets all of our criteria, and it is an alternating convergent series. Right? It converges by the alternating series test. Then we want to say, well, what about if we took an absolute value? What would happen to it? So then we'd be thinking about the series of just 1 over n and 3 to the n. So we can't approach it as geometric because of that extra multiplier of n in there. So if that wasn't there, we could approach it as a geometric, and then our ratio would just be 1/3. That would be convergent. But with that n there, I'm going to now approach this with our ratio test, which I've said before is actually my favorite test. So the ratio test says that we're going to take the quotient of plug in n plus 1 divided by the series as itself. Sorry, there are like bells and whistles all over the place right now. Sorry, that's really distracting. Now I end up with this fraction divided by a fraction, so I'm going to rewrite this. And that's going to be, if we think about dividing as multiplying by a reciprocal, flip over that bottom fraction, and I'm going to end up with this. Now when I go to cancel stuff here, I can cancel off all of those 3's except for 1 3 left on the bottom. And now as n goes to infinity, I've got n over 3n plus 3 if I distribute that 3 that's left on the bottom. As n goes to infinity, I would have infinity over infinity, but a L'Hopital's rule would lead us to 1/3. Now our ratio test says if that is smaller than 1, we have convergence. So this does converge by our alternating series test, and it also converged with its absolute values by the ratio test. So then we're going to say that this one is absolutely convergent. It's convergent in every way. It's convergent with its negatives. It's convergent without its negatives. So on that one, we used that ratio test from the last lesson. All right, one more example for you. All right, so as we think about our alternating series here, we've got that the terms are going to be positive, negative, positive, negative. They are not going to be getting any bigger after some point. And the last thing is that as n goes to infinity, would we get a value of 0? So as n goes to infinity, we would actually get a value of 1 here for the terms themselves. So this then we cannot apply that alternating test to. And so then we would maybe want to think about, well, what about if we took the absolute value of it? What happens then? If we take the absolute value of this and we approach it without those negatives, since as n goes to infinity, we get an answer of 1, well, that's actually our nth term test. Our nth term test is if n is going to infinity on this, we get an answer of 1. And the nth term test says if you get anything other than 0, we have divergence. So this is actually a divergent series, both with its negatives and without its negatives. If that 1 and 5 were reversed, so the 1 was in the numerator and the 5 was in the denominator, then we would actually be able to say it is conditionally convergent, because then the alternating series test would still work out for us because the terms would be not increasing, but in this point they are increasing. So this is, again, the last test that we're going to be learning. We've learned a lot of them, so I know it can be really overwhelming. Just make sure you're asking me questions as you have them. I'm happy to help through email or however else you want to contact me so that I can try to help you out with these series. Talk to you later, guys.